like that. Instead, what we're going to do is we're going to re-engineer the way password authentication works on the web. By way of preview, we're going to do client-side hashing. We're going to use an HMAC for authentication. We will talk in detail about what that means later. And we're going to add a lot of resistance to some of the common attacks against passwords as they are used in the web browser. Now, this is a perennial topic of conversation, client-side hashing specifically on Stack Overflow and on every other programmer discussion site on the web. Most of the sources there agree that it's a bad idea. But we have two improvements over the way that this is usually discussed. We're going to actually move the password form out of the DOM, out of the web page. And, well, like I said, we're going to use an HMAC to authenticate instead of just sending the password over the wire. So this is going to be fairly technical. Feel free to shout out questions or anything like that. So like I said, I work for Parameter Security. I primarily play offense. I break into web applications. I break into network servers. When I do research and teaching and speaking and training, that is usually on the defensive side. So I train programmers and stuff like that. My alphabet soup resume is on this slide if you care. Most critically, I'm not a cryptographer. I don't have a PhD in crypto or any kind of degree in it. No formal training whatsoever. And to be honest, I'm probably not qualified to have opinions on the subject. That being said, let's talk crypto. So, let's start by addressing an important threshold question. There are a lot of folks out there who think that password security is just not a thing anymore, or it won't be very shortly. Either because A, passwords are about to go the way of the dodo bird, or B, technologies like multi-factor auth, etc., are going to mean that password security just doesn't matter as much anymore because there are other hoops you have to jump through to compromise an account. I disagree. I think multi-factor auth is a wonderful development. I think its more widespread adoption is going to be fantastic for InfoSec. But password security, in my opinion, still matters, and it is going to matter for a very, very long time. And so let's take care of an easy one really quickly. Who here thinks that biometric auth is going to mean passwords are done? Or they're not going to matter? Okay. I won't preach to the choir, but the argument goes like this. What happens when someone creates a model of your face good enough to fool a facial recognition scanner? You will be forever and irrevocably hosed the moment your biometric identity gets compromised. Kick that one out the door right now. But the standards that I think provide the best argument for the passwords don't matter anymore crowd are a set of standards coming from a group called the FIDO Alliance. And let's talk through them just a little bit to show what they do for authentication and security. The basic idea of these systems is that we have a public-private key pair that usually is stored on a USB token that looks just like that. Anybody have one of those? A Yubico key? Mine's right here. Love it. Excellent. One of the best security purchases I've ever made personally. And so the basic idea is that when you enroll this device in your account, you send the public key to the server that stores your password and everything else. And then when you want to authenticate, you plug this into your computer, you perform a physical gesture, you touch that gold key in the case of a Yubico key, and then your client cryptographically signs a challenge message and sends that signature back to the server. This provides all kinds of security benefits. Perhaps most importantly, there's nothing to phish. There's no secret that the user is typing in that we can trick them into telling us. There's nothing to sniff off the wire. If we do sniff it off the wire, all we've got is a single signed message. We can't reuse that for future authentication attempts. And so there are two different ways that these standards can be deployed. First, there's the U2F standard, which is universal second factor. It's just a second factor of authentication, something you have that complements the password, which is something you know. Very, very good. All right, class is in session. So if U2F is adopted universally, passwords do become a little less important, arguably. And you can also use this key as a single-factor, password-free authentication system. People have been doing this for years. I think back in 2014, I want to say, someone implemented password-free authentication using the Secure Enclave on the iPhone and using undocumented API functions that let you do exactly this. And of course, Webauthn is the name of the standard that integrates this into a browser. It's worth knowing. So, with all this, is the FIDO Alliance going to kill passwords? And I think the answer is no. First reason, Webauthn, the standard that lets us do this in the web browser, is a baby standard. It's less than 3 months old. right? The crypto that lets us do that, by the way, very old. The RSA paper, the paper that announced one of the most important public key crypto systems on the planet, it was published in 1977. The movie Smokey and the Bandit was still in post when this cryptography came out. And that is a lesson worth learning, that it's not the technology, it's not the crypto, the math that prevents us from doing good things with auth and other types of security. It's the standards, it's the documents and the rule sets by which we agree how to deploy this in an interoperable manner. I think that's true across the board. So it's far too early to say that passwords are going to be murdered by the FIDO2 authentication system. Anybody have a service where there's a remember me next time option where you don't have to insert your USB key? You don't have to do the second factor? There's a potential bypass mechanism. What happens if you lose your token? Cost you more to replace it? Might be harder to regain access to your account depending on exactly how it's deployed. And let's also be honest, the people in this room, we're all interested in security, at least somewhat. How many of the average users do you think are really going to be that interested? Now, I'm going to get up on my soapbox a little bit. As security professionals, yes, it is our job to evangelize, to preach the gospel of security, and to encourage people to build good habits. But at the same time, it's also our job to meet people where they are and make the digital world a safer place, even for people who don't always take our advice, which is everybody. So, dismount. Passwords. One of the biggest benefits of passwords is that they are ultra portable. Any place you have a keyboard, you have the ability to enter a password. You can borrow somebody's phone. You can go to a conference center and use their public computer and type your password in, which does have its own set of security risks, no doubt. But in terms of accessibility, passwords really can't be beat. And of course, password breaches can be remedied quickly. Hell of a lot easier to get a new password than to get a new face or to get new fingerprints, even if you live in the Men in Black universe. So in short, my opinion on this, until this is what Google's registration page looks like, until we see insert your hardware security key and press the enroll button with a tiny little option underneath that says, oh, use a password instead if you want. Until this is the world we live in, we need to care about password security. That's my humble opinion. So, with that question addressed, let's look at the way passwords are done in the web browser. The web don't password good. That's my opinion. And the core of the reason why is that we send the password across the wire every single time we authenticate. So, Dave Vaughn, actually in Imagination, is talking about attacking passwords, doing offline attacks, cracking dictionaries, all that kind of stuff. But this is what it looks like from the defensive side. If you log in, you literally post a request to the server that says, here's my username and here's my password. The server pulls the salt out of the database. Salted hashes are designed to prevent precomputation attacks. You deny the attacker an economy of scale because, in short, you have to attack the passwords one at a time. So two users could have the same password, and because we add a random string to the password before we hash it, those two passwords, even though they might be the same, they might have different hashes. That's a brief summary of why we salt passwords. So what's the problem with this? What's the problem with sending passwords across the wire like that? Well, all kinds of things. It's capital B bad. There are flaws in the transport layer all the time. Now, I'm not talking about plain text HTTP. Who in here uses plain text HTTP for any production service? Who's willing to admit that out loud? Nobody. Good. What is the free source for SSL certificates? Anybody know? Let's Encrypt. Yes, everyone in this room should know about Let's Encrypt. It makes SSL TLS so much more accessible, and it is an absolutely indispensable part of the web security ecosystem. There's a buzzword for you. So, flaws in the transport layer. Who remembers Heartbleed? Anybody ever popped it in real life? Anybody ever exploited it and gotten some useful information? Yep, we've gotten passwords before. Just having the password in RAM can be dangerous. CAs can be compromised. It has happened more than once. Trustico, not too long ago, in February 2018, it was discovered that about 500 rogue SSL certificates were issued by that CA. It's a big ol' honkin' mess to clean up. SSL certificates are the foundation of the trust that makes the web work. And when that trust is compromised, holy goodness, do you have problems. So the transport layer can betray us. Side channel leakage. Twitter and GitHub both had recent problems with passwords. Anybody know where the passwords were leaked in plain text? Log files. Passwords are stored in plain text in log files. Now, as far as I know, they didn't have evidence that anybody actually stole them, but that is a big, glaring security hole to have them just sitting there in plain text. Rogue JavaScript all over the place. Cross-site scripting, for example. Anytime there's malicious JavaScript running in a browser tab, the creator of that JavaScript can mess with you. They can present you a fake-looking login form, or if they XSS another site, they can literally use JavaScript to capture your keystrokes one at a time and phone them home to another server. Just out of curiosity, when I was prepping this, I went to yahoo.com and tracked how many different JavaScript files were loaded and executed in my browser with all my ad blockers off. Any guesses as to how many? 50? Anybody else?
5,000.
Not 5,000. So more than 50, less than 5,000. It was 173. Loaded from 17 different domains. If I'm an attacker, that's a big attack surface. I got a lot of different SSL private keys I could compromise, a lot of different web servers I could pop and control that JavaScript running in your browser. And of course, the big granddaddy of them all, phishing. Phishing is one of the biggest attack vectors in real breaches. And one of the reasons why it's so dangerous is that those of us who have good passwords, who's proud of their password in here? I am. The password to get into this laptop right here is like 40 characters or something like that. It's a decent password. But if someone can phish me, so long as we're sending passwords in plain text over the wire, if someone phishes me, they got my password no matter how strong it is. Now, passwords present a very unique security problem. They are used for authentication, but we all know that people, including our beloved users, reuse passwords. So, a password, if you steal it, can not only get you into the account where you found it, it can get you into other accounts. A password from Twitter might get you into someone's, Charles Schwab account or into their yachts.com account or whatever else it might be. Now, passwords obviously aren't the only sensitive thing we transmit over the web. We transmit social security numbers sometimes, credit card numbers, whatever else people care about keeping private. But passwords, there's a certain automaticity with the way we type them in. We see a login prompt, our fingers are used to typing in our password. So you don't have to think about the letters and numbers you're typing when you type your password sometimes, if it's a password you used for a long time. Anybody else experience that, where your fingers just know what to type and you don't have to think about it? That makes it a lot easier to get someone's password than to get their social with phishing. Well, that happens as well. Can you think of another protocol that we use as frequently and that we do as many different things in than HTTPS? Does anybody bank over SSH? Does anybody do online dating through SFTP? Not that I know of. Phishing is a silver bullet and it's a dangerous one. But the unique aspect of passwords that works in our favor is that technically speaking, the server doesn't have to know what your password is. They don't even theoretically have to have the hash of it. All they have to have is a way that is cryptographically sound of verifying that you have the password. That's going to be what we rely on when we build our better authentication system. Now, like I said, there are a million Stack Overflow threads about this. Here's the way people typically suggest doing client-side password hashing. You send the salt to the browser when the user types in their username. JavaScript running in the browser does SHA-256 or PBKDF2 of the password and salt, and then submits that value in the form. This is how people usually suggest doing it. There are a couple problems with it, as people are want to point out online. When you do this, you're making the hash the password. The hash itself is the shared secret that you have to submit over the wire. So you're just, substituting one weak point for another in a way. And if you're doing this with JavaScript that sits in the browser, what happens if you've got an active man in the middle who can modify your network traffic? What happens if you're actually on a phishing site that looks like twitter.com but isn't? Your phishing guy doesn't have to put this JavaScript in there. They can just watch you type the password in and get it in plain text. So this approach doesn't really get you too much, but I really do believe that client-side password hashing can give us a lot of benefits, and we can demonstrate it. So let's build a better solution, a better way to do client-side password hashing brick by brick. So what attacks are we trying to prevent? First of all, we've talked about most of them already. Forgery of authentication data. We want to make sure that a third-party attacker can't forge whatever stuff it is we use to prove who we are. We want to prevent sniffing or passive man-in-the-middle attacks, and that can be somehow you have a network position where you can listen to what's going on, or if you record the traffic and find a way to decrypt it later, if an SSL private key is popped after the fact. That's why forward secrecy is a thing. So, active man-in-the-middle attacks are ones where the attacker can actually modify the traffic in real time. They can modify the way your web page works. They can add or remove JavaScript or do whatever. Phishing. The attacker impersonates the targeted site and then records the data you type in and uses it later. This is the big one, the granddaddy of all password attacks. And lastly, relay attacks. This one's going to become pretty important. That's where your attacker sets up a phishing site, but instead of just recording the data and using it later, behind the scenes, they're actually creating an active session on the targeted site and just passing through the authentication data that you submitted. We will go through that one in detail a little bit later. Goals, what are we trying to do with this new system? We want to resist all of these attacks as best as we can. Now, if we design a new authentication system, there's going to be a new set of attacks that we have to defend against. There are going to be some server-to-client attacks that we need to defend against, and we will do that. We want to maximize the cost of attacking a user and getting their password. And one of the biggest ways we do that is that we're going to set things up so that even if the attacker phishes us, sniffs traffic, whatever, instead of having the plain text password, they have some big old massive bytes. And to recover our plain text password, you're going to have to do what Dave Vaughn is doing in Imagination and run some kind of offline password attack. So even if my social engineering works as the attacker, I'm still going to be up against a difficult computational problem before I can actually recover your plain text password. We got to keep all the benefits of passwords, meaning we got to maintain portability. We can't have some extra device that we need to use. And for that reason, because all we're relying on is a password, we do not have access to public key cryptography at all. We have to use only symmetric encryption and/or hashing and other one-way algorithms. Basically, we're going to do our best impression of the FIDO standards using only a password. And yes, what we do here in this talk will take a lot of guidance from those standards, especially the origin binding feature, which we will get to. And we need to allow this system to roll over and replace the cryptographic primitives, meaning the hash functions. One of the biggest benefits of TLS, and one of the reasons why that protocol is going to stand the test of time, not only are cryptographers working on it and improving it, but you can swap out every single block cipher, every single hash algorithm, and you can swap out the key exchange method. TLS allows you to do that. So years ago, we used to use MD5 in TLS connections. MD5 is busted. It is super busted. We don't use it anymore. All we had to do, change a couple lines of configuration in your apache.conf file. So we want to have that flexibility as well to survive changes in crypto best practices. We are going to do challenge response authentication. This is critical because it prevents trivial reuse of authentication data. An attacker can't just write down your authentication data and reuse it on the same site. The tool we are going to use to prove our identity is called an HMAC, a hash-based message authentication code, also known as a keyed hash. The construction is a little bit weird and it looks artificial if you're looking at it for the first time. It's in an RFC if you're actually interested. The point is it basically does the same thing as a hash. It does a big mathematical computation that can't easily be reversed, except it uses a key in there, a secret key. And an HMAC, in effect, does a good impression of a digital signature. If someone you're talking to signs a message using a key, or rather, say that again. If a user you're talking to gives you a correct HMAC of a message you've just presented, you have good verification that the person you're talking to has that key, that pre-shared key. So that's why an HMAC is a good method of authentication, why it works. And again, HMACs have an underlying hash algorithm underneath them. We're going to use SHA-256 here. That hash algorithm can be swapped out. So, more concretely, here's what we're going to do. We are going to hash the password on the client side. To log in, the client is going to get a challenge message from the server. What is a one-time use challenge message also called? A short one-syllable word for it. Anybody know it? A nonce, yeah, is the general term I was thinking of, yeah. So we're going to get that challenge. The client is also going to get the password from the user, obviously. The client will compute the password hash, use that hash as the key to generate an HMAC of the challenge. To verify, the server is going to pull the stored password hash out and compute that same MAC and compare the results. Here it is visually. To start out, The browser visits the login page. The server then says, okay, ready to log you in. Here's your challenge message. I want an HMAC of it using your password. The user, the physical human being using the system, says, okay, browser, here's my password. The browser then computes the password hash, computes the HMAC of the challenge message, and sends that across the wire to the server. The password only traverses this gap here, which is the gap between a keyboard and something running inside your computer. But that something running inside the computer is not going to be a web page. It's critical, again, like we talked about, for this to resist phishing. And again, if this is implemented with JavaScript, all of our fancy crypto, our HMACs and our Elemento PQRSTs are implemented in JavaScript inside the DOM, any one of those 173 JavaScript files running inside your browser window can mess with it. So, we are going to create a form that exists outside the web page itself. We're going to use a browser extension to do it, unfortunately. We're going to set it up. We're going to take advantage of features of the Web Extensions API for Firefox and even Chrome that ensure that JavaScript running inside the browser can't forge these GUI elements effectively. We're going to set it up so that the user has to do an interaction with the browser so that they're confident they are speaking to the browser authenticator module and not the web page. Can anybody else think of another scenario where in order to log into something, a computer perhaps, you have to do something very specific with your keyboard? Anybody use a well-known commercial operating system called Windows? What keys in some configurations do you have to hit before you can log in? Control-Alt-Delete. And there's something very important about that key combination in the core Windows API. Anybody done any Win32 API programming at all? Okay, all right, thanks. So, in the core of any Win32 API program, you have what's called an event loop, a message loop, where messages from the operating system are passed to your code. These messages include keyboard events. And you can tell when someone presses Control-S. That's why Microsoft Word can save a document. You can tell when someone presses, I don't know, Control backspace. That's how Word can delete a whole word at once. The operating system will never pass you an event for Control-Alt-Delete. The core of the Windows operating system ensures that that gesture, that action of pressing Control-Alt-Delete, can only be trapped and responded to by the operating system itself. So, we're going to take a cue from that, and we're going to ensure, with our use of the Web Extensions API, that there's no good way for an attacker with a phishing site to convincingly forge the form elements. So again, even if the user visits a phishing site, our goal is for the attacker to be no better off than if they just sniff the traffic. The active man in the middle approach will add no value to the attacker's job, to the attacker's efforts, if the user is trained properly. So again, we're going to use a browser extension. We're going to use something called the native messaging API to do this. And if we have time and people, for some sick reason, are actually interested, we'll look at the code. But it's not a great feeling to implement the crypto in JavaScript. You know, we'd much rather implement it in native code. Fortunately, the Web Extensions API let us load a piece of native software on a client's computer and communicate with it in messages. Those messages exist completely outside the DOM. So the user will click a toolbar button, password form will appear in an extension pop-up, and malicious JavaScript cannot spawn it. Benefits, well, a summary, to just go through it one more time. And a demo is going to be coming soon. A server is going to present a challenge inside a web page. The browser authenticator is going to display its secure form. It's going to get the password and it's going to pull the challenge from the page. The browser authenticator will compute the password hash, that shared secret, and compute the HMAC of the challenge. The authenticator will put the HMAC back into the web page using the execute script API, and the user will submit the form. If the HMAC is correct, we'll log in. There are some important details to go through here. The devil is always in the details. We're going to need to construct this challenge message in a way that specifically prevents phishing and replay attacks. We also need to protect against certain attacks against the authenticator itself. There are some tricks a malicious person might use to try to get the authenticator to cough up something that's easier to attack than the HMAC we're intending to create. We also got to handle registration and password changes. That's going to be one of the weak points of this system, I'll tell you right now. And then finally we'll get to a demo. So, precomputation attacks, you might have heard of rainbow tables, are where an attacker goes through a dictionary and pre-computes the hashes of all these different passwords and stores it on their machine. If your hashes are not salted, that means an attacker can look up a password hash that they've stolen in constant time, meaning they can tell you exactly how long it's going to take to tell whether they've got that password hash in their database. And again, check out Dave's talk on Iron Geek if you want to know more about that, because I'm sure he'll be discussing it. So if the attacker, this expression here on our slide, HMAC of hash of password plus salt and the challenge, that is the expression we're computing. If the attacker can pre-select both a salt and a challenge, the attacker can pre-compute the whole thing. So they can build a rainbow table and pre-compute password hashes for our authentication system. We need to protect against that. We got two tricks we're going to use to do that. First of all, we're going to add a timestamp to the challenge. That challenge message is going to include a 32-bit integer that represents the timestamp on the server. That's going to protect against precomputation attacks. And the client's going to have to allow for some time zone differences, but, you know, that is very doable. And it also protects against accidental reuse of the challenge parameters if our random number generator for some reason coughs up the same number twice. Second, and most importantly, the client is also going to select a portion of the challenge message. Who here is familiar with NTLM authentication or SMB? Anybody seen those protocols? SMB does that as well, at least with NTLM version 2. Both sides select the challenge. What's the attack that the server could do if they controlled all the parameters? Well, at the very least, it's a precomputation attack. So, and the crypto theory term, all chosen plaintext attacks are going to be shut down by this whole procedure because the server can't select the whole plaintext that we're going to generate the HMAC for. All right, relay attacks. This is one of my favorite examples of an attack against this. Let's say a bad guy sets up a phishing website and convinces you that they're the good guy. If we just have these parameters that are selected by the server and the client, the bad guy can just pass through those parameters to the other end of the connection. They will set up a real connection to the legitimate website, and things happen in this order. First, we get a challenge from the server. Then the client sends a challenge to the server. So if I'm the guy in the middle here, I can just take the server challenge I was presented with, pass it along to the browser. When the browser authenticates, I can take their challenge, pass it along to the real server, and suddenly I have actually successfully just replayed authentication data, or relayed rather, authentication data from my legitimate browser to the server. I then have full control over that connection. They're going to interact with me thinking I'm a legitimate site, and on the back end, I actually have a live session with the real site. And at that point, I own the victim's account. I don't own the password, but I own the account at this point. So it can't be so simple to just pass through all those parameters. And there's a trick that we're going to borrow from the FIDO standard. And that is going to be that we will use the origin string as part of the challenge as well. The origin is a piece of the DOM, the document object model, the model you interact with when you write JavaScript that runs in a browser. This origin string is already really, really important for web security because it's part of the same origin policy. Any web programmers in the crowd? No? All right. So the same origin policy, the same origin policy prevents JavaScript from just arbitrarily sending requests to another domain and reading their output. That's why we can't just plop down an image tag at, gmail.com and use JavaScript to read the output and just read your mailbox. We're going to do the same thing. We are going to put the origin string, which is going to look like this. It will have a protocol handler and a domain name. If we're using a non-standard port for HTTP or HTTPS, the port will appear in the origin string as well. So this means that if our bad guy tries to do this here, with the origin binding feature enabled, the authentication data you get from the browser is only going to work for evil.example.com. You can't unwind all those computations and reinsert real.example.com and then relay the authentication to the real site. So origin binding protects against this kind of live relay attack. All right, so to summarize what we're going to put in the challenge message, we have a server timestamp, a 32-bit little endian integer is what we're going to do. We have the server challenge, we have the client challenge, and we have the origin string. The authenticator, the browser authenticator, computes the secret, which is the hash of the password plus the salt. The actual response, the actual message that gets sent to the server that gets checked, is an HMAC of the challenge message consisting of all this, using this secret as the key. Clear as mud? There are also some attacks against the authenticator that we have to prepare for. So, like we said, we want to be able to swap out the hashing algorithm, right? And have the authenticator use a better hash if we figure out there's a better one out there. That means the server has some control over the computations that the authenticator is doing. What if someday somebody figures out a trick to make the authenticator spit out a hash or an HMAC that happens to be very easy to attack because of some weakness that some cryptographer somewhere figured out? We're going to have to prevent against that. So there needs to be a floor on the configuration of all these hash algorithms. There need to be certain minimum standards. In our case, we're going to use the Argon2 password hashing algorithm. In 2015, it was the winner of a password hashing competition run by a team of cryptographers. It is a memory hard function like bcrypt, meaning that not only do you need a lot of CPU or GPU cycles to attack this hash offline, you also need a lot of memory. And the algorithm is designed so that it's not easy to just exchange memory for more time. And of course, Moore's law does not apply to RAM. Processor speed doubles every 18 months. RAM does not get half as expensive every 18 months, and it doesn't get twice as fast every 18 months. So, we're going to take advantage of that, or the creators of Argon 2 took advantage of that when they designed it. There are 3 parameters that you have to choose whenever you're implementing Argon 2, unfortunately. How many iterations you're going to do in all of the magic that happens inside the box and arrow diagram, how much memory you want to force the authenticator to use, and how many threads are going to run at once. This is another interesting illustration. The minute you make something confusing or difficult to use, the minute you give somebody a choice that they have to make before they're going to use your product or your tool or your standard, they just get that much more likely to say, forget it, it's not worth it, I'm just going to go back to using MD5. So, again, remember, as security professionals, we always have to put ourselves in the user's shoes. We need to make things easy to use. We need to make them accessible. And we need to anticipate some resistance to what we do as security people. So, anyway, we are going to use SHA-256 as our hash algorithm for the HMAC itself, for that second step. SHA-256 is unbroken, as far as we know. Other password operations. So, of course, we have to log in, but we have to also be able to register. We have to be able to do a password reset. So you get the password reset link in your email, and you click on it and you submit a new password. Password change is where you're already logged in. You re-authenticate by typing in your current password, and then you provide a new password. Everybody who writes any kind of authentication system is requiring their users to log back in before changing their password, right? Right. Okay. So again, these other operations where we have to actually send the secret to the server, enroll the secret, so to speak, are going to be one of the weak points. But we have ways to do it so that it's relatively secure. So let's get to the demo. And I've prepared for the demo gods to try to ruin my day and make this demo not work. I have a pre-recorded video of all this going on. So, and of course now I get to go wrong with the microphone mounted on the table, which is always fun. Actually, you know what? No, I'm going to hold it because you can't hear me there. All right, so a bit of what we've got on the screen in front of us. That big old square is the magnifier. We've got a demo sitting here in our browser, a demo of this whole system. I am shocking. The minute I talk about having beaten the demo gods, my network connection drops. I deserved that, I think. I begged for that to happen. All right, so here's what we're going to do. We're going to see it. We're going to give this one go, and if not, we are going... All right. Which one of you created an access point called not ShowMeCon? I was almost fooled by it, I swear. All right. Anybody know what the passcode is for this? It's casino. I kid you not. That is, the 4 years I've been at this con, that has been the running joke of the conference. So, let's try this one more time, see if we can get to our demo here. So I am really bad at a lot of things, and among them, I am bad at coming up with names for things. So right now, this system's called Crassword. So we will give this one more go. Hang on. All right, there we go. So, just to look at the lay of the land again, we have on our right Burp Suite, which is going to let us look at our HTTP requests and responses. And on the bottom here, we are doing tail -f on a log created by our native messaging host, the component that actually does the crypto stuff for us. So, we're going to register a new account here. Let's make the username, we'll just call it SMC. All right? Now, the web page is telling us use the Crashword extension to provide a password. Well, this little lock icon is our extension. All right? We click on it, and now we get this little form. Again, it exists completely outside the DOM. JavaScript running in the page cannot interact with this form. We will make our password the word test, because we're all about good passwords around these parts. Now, we see in the log that our Authenticator, the native messaging component, has done the crypto for us. And that message was passed from the browser extension to this native messaging host. The type is a new password. That's the type of operation we're doing. Test is our password, and here are the hash config parameters. So we're doing 6 iterations. Our exponent on the memory usage is 16, and we're going to do 2 threads. The hash is going to be 32 bytes long. The salt is being generated on the client side, which we need to do to prevent some of those precomputation attacks. So now, the web page knows that we've submitted the password, but all it's gotten there is that hash. It doesn't have the plain text password. So now we've registered, and let's look at what just happened in the background. This was our post request. We submitted our username, which is SMC, and we submitted the hash. We also submitted the salt that we generated on the client side. Nowhere in this request does the word test appear. This is the vulnerable point. We have to send the actual password hash to the server, but we never had to show the DOM or the server what our actual plain text password was. Gives us a lot of resistance against phishing. Now we will log in. We start off by providing our username, which was SMC. Now let's look at what just happened in the background. This request to Crashword config. So we requested some configuration information for SMC. The reason we have to do that in the background is we need to know what our salt is. We're recomputing the password hash client side, so we need to know the salt. Any geeks out there who can say why it's not a security problem for salts to be disclosed to the browser? To be a matter of public record, so to speak. Speed, well, yeah. The real reason why it's not a security problem, a salt's only job is to be different for every account. The salt does not need to be secret. All we're doing is thwarting precomputation attacks. So long as the salts are different for every account, the attacker has to attack these hashes offline one at a time. You deny the attacker that economy of scale. That's the only point. If I know your salt beforehand, doesn't help me. I still have to crack your hash one at a time. So, we have that config going on in the background here, so now we can use our extension. We click our lock icon, and now we just get a login form. We say submit password, and we get the operation happening in our native messaging host. We got a login request, our password was test, our salt was passed through from the server, and now we have our HMAC data down here. I will go ahead and zoom in on that. The server's timestamp was this 156 number. This value here was the server-side challenge, the challenge that the server gave us. This is the challenge component that we as the client created. And most importantly, well, not most importantly, but importantly here at the end is our origin string, demo.crashword.com. If they try to reuse this authentication exchange on twitter.com, ain't gonna get nowhere, because it's origin bound. So that HMAC was then inserted into the DOM. Client-side JavaScript in the browser knows that it has the token. It knows that Crashword has done its job, but it couldn't interact with the process of us typing our password into the Authenticator. We now log in, and there we are. We're logged in as SMC. We'll look at the post to the login method. All we posted was our username, the token, which was the HMAC, and the challenge that we generated on the client side. Notice that this value, 243DF, is the same as this component of the challenge message that the Authenticator generated an HMAC for. That was generated client side. So, now let's look at the other ones. When you change your password, so in this scenario, the password change means that we're logged in, but we just tell the application we want a new password. for our own reasons. The form now is different. We need to enter our current password, and we need to choose a new password. So we'll log in with test. We will use a longer password, and we'll click this change button. So down here we have a message in the native messaging host that says change password. The existing password was test. The new password was, lo and behold, a longer password. So now we see that our native messaging host generated that HMAC to log in, but it also just generated the hash for the new password. We just have to do both operations at once now. So we will now say change password. And oh no, it's broken! No, kidding. So again, we see both components happening at once in Burp Suite. We submitted our token, we submitted our challenge, which is exactly what we did when we logged in, and we also have the hash and the salt for the new password. So it all just happened at once. Again, completely outside the browser. The DOM never even sees the actual password. So we preceded the database with a password reset token. I don't know why I'm holding my clicker all the time. We will do reset token equals reset underscore SMC. That's totally secure password reset token, as you all know. So you notice at each step of this operation, the web page itself is taking a step back and saying, all right, I know it's time for you to do something with your password. I'll step back and let you talk to your authenticator alone. You know, it's a little bit like when your employer wants a note from you to make sure that you were actually sick when you were out for a week. They don't want to walk into the exam room with you and stick the little camera thing up your nose to see if your sinuses are actually clogged. They just let you and your physician do what you need to do, and I'll take the result once it's done. That's what the web page now has to do. The web page is not in the password handling business anymore. Our authenticator is. So, our new password is going to be bad. So now we again have that new password message. This operation is the same. Password reset is the same as registering a new account. Because it's just saying, I don't need to log in, I just need to tell you what I want my new password to be. So we reset it. Password's been reset. We can now log in with SMC. We'll go back to Crossword, and we can log in as bad. And we're back in. So that is the basic operation of this whole thing. Now let's talk a bit more about the impact. Man, you look happy. So we will go back to presenter mode, and we will restart our presentation. All right, our demo is done. So the good things. All right, what benefit did we get from this? The HMAC, this authentication token we sent, can't be forged barring a really deeply broken hash function. We have resistance to sniffing and passive man-in-the-middle attacks when we log in. We have resistance to active man-in-the-middle attacks so long as the user knows that they should only be telling their password to our authenticator. If the user behaves the way we want them to, they won't even tell their password to a malicious web page. I know that's a significant ask of the user. We also have resistance to replay attacks and relay attacks due to origin binding. And we have, in general, if a bad guy wants to attack us, they have to not only spend more money to do it, they have to use multiple techniques at once. They might have to social engineer us and have a cracking server. The bad. Yes, we have indeed made the hash the password. The hash is now the shared secret we're using to authenticate. We do have to send it over the wire when we register or change the password. If the attacker does sniff the hash in transit, they are able to compromise the account. Now notice that they don't have the password, and even if they trick us into registering on a malicious site, we're not going to have given them our hash for the real site. Reason being, salts are generated client side. So long as there's no collision in our two salts, even if we use the same password to register on two different sites, the actual shared secret is not going to be the same. So again, the operations that set the password are the closest thing to an Achilles heel we have. We are preventing reuse of the F hash. That's a new development in the mathematical community. It's like an F stop. It's an F hash. I'm kidding, it's just a typo. So, what the folks on Stack Overflow, yeah, I know. I'm trying to liven things up here. We're talking about cryptography. It's the most boring thing on the planet. So this is actually the most interesting weakness of this system. If the bad guy actually pops our database and gets our password hashes, they can actually log into every account now. That is the biggest weakness of this whole system. In a normal, traditional password hashing system, if the bad guy compromises the authentication database, they still got to crack the plaintext password, because you have to send the plaintext password across the wire to log in. Here's my argument for why the phishing resistance we get outweighs this weakness. If the bad guy has compromised the authentication database, that's probably not the only thing they've compromised. You've probably already got really huge problems on your hands. So increasing the impact of a total database breach a little bit by allowing the bad guy to log in immediately is not that much. There's not that much space between those two scenarios, because the bad guy has probably already compromised a lot of data that's caused you a lot of headaches with HIPAA and GDPR and whatever else we care about. The ugly. What do we do about mobile? What about this whole password portability thing? Mobile devices have a keyboard, right? Problem is, they don't have the native messaging API. It's just a completely different animal in terms of writing a browser extension. So that's something that needs to be figured out, and it probably is going to mean that the browser has to be rewritten pretty significantly. And we need to be able to support other user agents. What about wget? Command line browsers. I use them, they matter. So that actually sounded really arrogant. If I use them, therefore they matter. But I don't know. Anyway, those programmers, those developers and maintainers are probably going to be a little slower to adopt this, which may impact our ability to make this universally usable. We don't want to be using an extension to do this. And again, the resistance to phishing is behavioral at its core. It requires the user to get used to communicating only with Crashword, with our Authenticator, when they're typing their password. In order for this to work, it has to be adopted across the board, or at least as broadly as possible. Users need to know what that means when they click that lock icon, and they need to know instinctively why it's dangerous, that it is dangerous, and that they shouldn't be typing their password directly into the web page. So the way forward for this, and this is just a random research project that hopefully made interesting conference talk fodder, but if this actually is going to work, cryptographers need to pay attention to it. We need some professionals to actually vet the crypto. Again, everyone, including me, likes to give the advice, don't roll your own crypto. And we tried to minimize the impact of it in this. That's why we didn't try to replace the HMAC algorithm with something new. We just used a standard implementation of RFC 2104. But we need some attention from cryptographers. This needs to be written into a formalized standard. It needs to be portable, and it needs to be written so that any browser developer, be it Brave or whatever other new browser is on the block, so that they can make their browser work with this standard as well. It needs to be core browser functionality. And we obviously need to have major vetting on the code that actually implements the crypto, because it takes years and lots of effort to avoid timing leaks and other side channel problems with code that does cryptographic functions. So that is the way I would like to see password authentication done on the web. I think there are real concrete benefits to it, and if anybody knows someone on the Mozilla developer team, send them a link to this talk after it's up on Adrian's website. Have you got any questions? We have 53 seconds left. All right, I will be around. I'll be at the Parameter booth at some point if anybody wants to come talk. Otherwise, thank you very much. Enjoy your day.